So chemical reactions. We've talked about chemical changes. Chemical reactions involve chemical changes. We have existing substances being destroyed and new substances being created. In that process, what happens to the atoms is that they become rearranged, like Lego blocks when you take a structure apart and build something new. The blocks themselves are unchanged. In a chemical reaction, the atoms do not change. They just get mixed around. So the same atoms you start with are the same atoms you end up with. Okay? That's a really important concept. We use chemical equations as a shorthand method of representing chemical reactions. And the general form is that we have the reactants on the left side and an arrow pointing to the right where the products are. The reactants react to produce the products. Okay? In the equation, there is a lot of information. The formulas for the reactants and products are given. Often the physical state, solid, liquid, gas, aqueous, are given. Relative numbers of reactant and product molecules are given. And from that information, we can figure out, well, if we started with 10 grams of this reactant, how many grams of the product could we make? And that is a very practical sort of calculation. These are the state symbols that are used in chemical equations. These are put in parentheses immediately following the chemical formula. So G for gas, L for liquid, S for solid. AQ means aqueous. It's dissolved in water. So let's look at the combustion of methane. Methane is a major part of natural gas. So you have a gas stove. This chemical reaction occurs when you light it. When we light the Bunsen burners, we've got this chemical reaction. Whenever something burns, it combines with oxygen. Okay? Combustion and burning, same thing, requires oxygen. So here's methane, and it's a gas at room temperature. It's going to react with oxygen, that's a gas at room temperature. Now, how do you know that oxygen is a gas? Well, most of us recognize oxygen as being something in the air that we breathe, so we should guess that it's a gas. The periodic table can help us out with this as well. On the periodic table on the wall, anything with its element symbol in red is a gas at room temperature. Anything with the symbol in black is a solid at room temperature. And there's two that are blue, mercury and bromine. Those are liquids at room temperature. So if you need to put a state symbol in for an element and you're not sure what it is, check the periodic table. Unless it specifies or indicates otherwise, you can assume that it's happening at room temperature. Then the products are going to be CO2 and water. This is a reaction that generates a lot of heat. It's burning natural gas. The reason we do that is to generate heat. So the products are going to be hot. So that's why water is in the gas state here instead of in the liquid state. So here are the reactants and here are the products. Now the problem is that if we look at the individual atoms, we've got 2 oxygen atoms on the reactant side, 2 oxygen atoms here, and another oxygen atom over here. You can't start with 2 oxygen atoms and end up with 3. It's just not possible. You can't start with 2 red Lego bricks and end up with 3 red Lego bricks, right? It just doesn't work that way. Another problem is with the hydrogens. So on the reactant side, there are 4 hydrogen atoms here, and on the product side, there are only 2. So a creative person might say, well, maybe those 2 missing hydrogen atoms turned into an oxygen atom. That would make everything good. Well, that's a nice idea, but it doesn't happen because the atoms do not change their identity. Okay? So the equation as it's written here is going to violate the law of conservation of mass. So does that mean that nature is wrong? No, it means that we wrote the equation wrong. We need to fix it. So we need to do what's called balancing the equation. We balance it by changing coefficients. So coefficient is a number that we put in front of the chemical formula. So 2O2 means I have 2 oxygen molecules. They are each O2, and I have 2 of them. 2H2O means 2 water molecules. Okay? You put coefficients in, you can change those. You cannot change the subscripts. You can't decide that if I put a 4 here, that it would balance the hydrogens, H4O, because that would change what the reaction is doing, and we can't do that. Okay? So it helps to think of these molecules in terms of their models. So they're like Lego, chemistry Legos, right? They're round instead of little squares. So here we've got 4 white balls. So in the products, however they're arranged, we need to have 4 white balls. And we do that by saying there must be 2 water molecules. Over here, we're going to say there's 2 of these so that we have 4 red balls. We've got 2 red balls here and 2 red balls there. So we've got the same number of red balls on each side. There is 1 black ball over here and 1 black ball over there. Okay? So that's the idea of balancing an equation. We want to have the individual pieces, the same number of each kind on each side. Any questions? If you understand this picture level, then it makes the actual balancing much easier because you can visualize what this formula, what this chemical equation is representing. Otherwise, it tends to be sort of a mysterious thing. So how do we go about balancing equations? The first thing you need is a skeletal equation. You need the correct chemical formulas for the reactants and the products. Then we use a method called balancing by inspection. And so it's recommended that you leave any elements that exist as free elements to the end and do things that are in more complicated things first. So, that is true. It also often works just to start with the first element. It's sort of a trial and error method. So start with the first element and work your way across. If things start to get messy, first double check that your equations, your formulas are correct. And then if they're correct, then maybe just start over somewhere else. Because, there's some things that it's easier if you go this way than if you go that way. Well, you don't necessarily know when you're doing it, right? So you start out and you realize, okay, this is not the easy way. Let's go back and go the other way. You can end up with fractions as coefficients. Most students don't like to do that. A lot of students think that fraction is an F word. So you would have to clear the fractions. The coefficients need to be whole numbers, and they should be the lowest ratio. And then you should always check your work at the end, because sometimes you overlook something. And if you go back and check your work at the end, you can catch that mistake. So let's do a couple of examples. These are also going to give us some practice in writing formulas from names of compounds. So write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. Okay, it's like this is sounding like real chemistry now, right? So that's a bunch of words. We need to interpret the words. So the words "and" are like a plus sign, right? This and that, this plus that. And the words to produce, that's like the arrow. So we can go in here and we can say, okay, it's silicon dioxide plus carbon to produce silicon carbide and plus carbon monoxide. So now we've got the words. We need to write the formulas and stick the pluses and the arrows in there. So silicon dioxide. Remember, when you're writing formulas or naming, the first thing you need to do is identify what kind of a compound. And so looking at the first element can help. Silicon dioxide, it's obviously not an acid, right? So it's either ionic or molecular. You find silicon on the periodic table, it's on the non-metal side of the line. Even though it's a semi-metal, it's on the non-metal side. So this is a molecular compound. And so silicon dioxide, we're not looking at charges on anything. We're using the di that tells us there's 2 oxygens. So this is SiO2. And the state symbol should be what? S for solid. Because they told it to us in the sentence, right? So then we've got a plus, and I'm going to leave a little space here because I may need to put a coefficient in there. Solid carbon. Well, carbon's an element. Its symbol is C, and it's a solid. Whenever you have an element, you need to ask yourself, is it one of the 7 diatomic elements? No, it isn't. Chlorine is a diatomic element, but that's Cl. Carbon is not diatomic, so it's just C. And then we have our arrow. And then silicon carbide. So that one's kind of tricky. So, hey Siri, what's the formula for silicon carbide?
Okay, I found this on the web for what's the formula for silicon carbide. Take a look.
Okay, she disappointed me again. Last spring when I did that, she would read it to me. So she did give me the formula, but she won't say it anymore, maybe because I laughed at her too many times. That's the formula for silicon carbide. She would say, the formula for silicon carbide is sick. I don't know, I just found that really humorous. Doesn't work anymore. Anyway, silicon carbide. Now, how would you get that with what you've been taught? Okay, that would be a little tricky. They're both nonmetals, so it would be considered a molecular compound, but there's no prefixes at all. So if there's no prefix, what's the only numerical prefix that we leave out? 1. So you could assume that, well, there must be 1 of each because there's no prefixes. I would not do that to you on a test. I don't think that's very nice. Did you have a question? And then we're told that it's solid. Carbon monoxide, you should be able to do that one. CO. Again, I'm going to leave a space and write CO. Make sure that's a capital O, and then that's a gas as well. So there's the skeleton. Now we need to balance it. Make sure there's the correct number of each atom on each side. So let's just start at the beginning. Here is silicon. On the left side of the arrow, how many silicon atoms are there? 1. And on the right side, 1. Okay, so it's balanced. Let's look at the next element. Oxygen. How many oxygens over here? 2. And how many on this side? 1. So I can fix that, not by changing the formula, but by putting a 2 in front of the formula. I must have 2 carbon monoxide molecules, because that would give me 2 oxygens. And then it's a good thing to think about, well, did that change what I've already fixed? Did it change the silicon? No, it didn't mess up the silicon. So we're good with the silicon and the oxygen. Now we're going to look at carbon. There's only 1 carbon here. How many carbons on this side? 3, right? There's 1 here, and there are 2 there. So you have to look at the carbons in all of the products. So I need 3 on the left side. Oops. So I'll just put a 3 in front of the formula for carbon. Any questions? So that's balancing by inspection. If you need a more visual or tactile approach, I give you permission to go out and buy some gumdrops or jelly beans or M&Ms or something. And just say, okay, the red M&Ms are going to be silicon, and the blue ones are going to be oxygens, and the green ones are going to be carbon. And make piles. And actually see, does it work out? Could I combine these? And that's a really good visual way of helping you to understand what's going on with the atoms, just rearranging themselves. And then when you're done, you can eat them. Let's do another one. Write a balanced equation for the combustion of gaseous ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. There's a lot of gas going on there. So again, and or combines with corresponds to plus sign. So combines with, ethane combines with oxygen. 2 form, arrow, carbon dioxide and water. So we need the formulas for these things. Gaseous ethane. I haven't taught you how to name or write the formula for ethane, so it's given to you there. So C2H6. And it tells us it's a gas, so that's all good there. Combines with gaseous oxygen. Well, oxygen is O, and it's a gas. Is oxygen a diatomic element? Yes. Horses need oats, or have no fear of ice cold beer. So it's the O. So all of those 7 diatomic elements, if they are by themselves, it's O2. If they are with other elements, then you don't write the 2. Okay? It's just when they're alone. Oxygen atoms, like junior high girls, do not like to go anywhere by themselves. And so they'll go with a friend if they can't go out with this group. Okay? Hydrogen's a diatomic element, but over here, that doesn't matter because hydrogen is with this group. Other hydrogen atoms and carbon, and so it is what it is. Okay, so we've got the arrow. It forms carbon dioxide, so that would be CO2, and we're told that's a gas. And water. Water is H2O, because it is, and that's a gas. It's going to be a gas here because this is a burning reaction, and so it's hot. Okay, so we need to balance this. I'm going to show you a different method of balancing. This problem is a little more complicated. If you just start out the balancing by inspection thing, you might find yourself going in circles for a while. So this is just another strategy. Some students like this, some don't. So use it if you like it, don't if you don't. So what I'm going to do is I'm just going to draw a line through the arrow, visually dividing the reactants and the products, and then I'm going to take inventory and see what I have on each side. So I'm just going to list the elements over here in the order that we come to them in the equation. So there's carbon, there's hydrogen, there's oxygen. Carbon, hydrogen, oxygen. And then below each formula, I'm going to just indicate how many atoms there are. So in C2H6, I have 2 carbon atoms. And there are 6 hydrogen atoms, and there are no oxygen atoms. I used to put zeros, but they look a lot like O's, so I'm just going with a dash. There's nothing there. In O2, how many carbon atoms? No carbon atoms. How many hydrogen atoms? None. How many oxygen atoms? 2, right? This is O2. You guys with me? Kind of sleepy this morning. Then over here, CO2. Well, that has 1 carbon and no hydrogens and 2 oxygens. And H2O has no carbons, 2 hydrogens, and 1 oxygen. See what I did there? Okay, now I'm just going to start at the top and move my way down, and I'm going to look at carbons and see, is it balanced with respect to carbon? No, because on this side, I add this, and I get 2, and over here, 1 plus nothing is 1. So I need to increase the number of carbons on this side, and so I'm going to do that by putting a coefficient in front of CO2. If I put a 2 in front of it, then I'm going to have 2 carbons. So I change this to a 2. That also affects the number of oxygens. How many oxygens do I have now? I have 4 in the CO2, a total of 5. So my carbons are balanced. Now I'm going to look at hydrogen. Are the hydrogens balanced? No. I have 6 on the left and 2 on the right. How do I make a 2 into a 6? I multiply by 3. So I'm going to put a 3 here. That changes the 2 to a 6, and it changes the 1 to a 3. I am multiplying these numbers by the coefficient that I wrote up there. So 3 water molecules, there are 6 hydrogens and 3 oxygens. So my hydrogens are balanced. I did not change the carbons, so that's fine. Now I'm going to look at the oxygens. Okay, I have 2 oxygens on the left side. I have 4 plus 3 is 7 on the right side. How do I make 2 into 7? by multiplying. Okay, so that's one that leaves students like, what? I don't know. You could use a fraction. This is how you can end up with fractional coefficients. If you multiply by the fraction 7 divided by 2, 7 halves times 2 is 7. Okay, so that's an entirely decent way to do it. Most students don't like that. The ones that do don't need my help figuring it out, so I'm not going to go over it anymore. So this is what I call the odd-even problem. Over here I have an even number of oxygens. These are coming in pairs. You can't buy pairs of shoes and get 7 shoes, right? You could get 6 or you could get 8, but we need 7. So what I'm going to do is I'm going to change this odd number into an even number by multiplying by 2. If you multiply an odd number by 2, it becomes an even number. So I don't want to mess up everything I've already done. So I'm going to go through here and multiply everything I've already done by 2, and then it'll still be balanced. So I'm going to multiply this by 2. That changes that to 4, changes that to 12. This is the one I'm messing with. I'm going to leave him alone. I haven't fixed that one yet. I'm just going to deal with everything else. So I'm going to change this 2 to a 4, and that changes this to 4, and it changes this to 8. 4 CO2 molecules are going to have 4 carbons and 8 oxygens. And then over here, I have to double this as well. That's going to be 6 water molecules, so I'm going to have 12 hydrogens and 6 oxygens. You okay with that? Yes?
If we like the 7 halves, then do we have to do the 6 halves?
If you like the 7 halves, you'd write 7 halves in here, and then you have to clear the fraction, go through and multiply everything by 2. So you end up doing the same thing. It's just a different way of thinking about it. So now when I look down here, well, carbon and hydrogen are still balanced because all I did was double the number on each side. I have 2 oxygens here, and I have 8 plus 6 is 14. Oh, well, now this is doable. If I multiply 2 by 7, I'll get 14. So I put a 7 here, and that changes this to a 14, and now it's all good. So that's sort of a tally method of balancing. Okay? Any questions? Let's do one with polyatomic ions. Write a balanced equation for the reaction between aqueous lead-2 nitrate and aqueous potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. All those words. Well, we've got lead nitrate and plus potassium chloride to form, there's my arrow, lead-2 chloride and plus potassium nitrate. Now, these examples have all had 2 reactants and 2 products. It doesn't have to be that way. You could have 1 reactant and 5 products. I mean, there's all kinds of different variations. So we need to write the formulas for these ionic compounds. And for ionic compounds, we need to know the ions with their charges. So we'll start with the first one, lead-2 nitrate. Okay, so that's got the lead-2 ion. The 2 is the Roman numeral 2 tells us the charge. It doesn't say that we have 2 lead ions. It says that the lead ions have a 2 plus charge. So that's lead-2. And nitrate, we memorize, NO3 minus. Once we have those formulas with the charges, we can look at their relative charges, and we see that we need 2 nitrate ions to go with 1 lead ion, so the charges add up to 0. So over here I've got Pb. I need 2 nitrate ions, and that's a polyatomic ion, so I'm going to put that in parentheses and put the 2 on the outside. It's aqueous, so I'm going to put AQ as the state symbol. Plus potassium chloride. Again, I need to look at the elements and their charges. So potassium is K. What's the charge on a potassium ion? +1, because potassium's in group 1 of the periodic table. And chloride is Cl minus because it's in group 7 of the periodic table. You come back from group 8. It's -1. So +1, -1, we don't need to do any cross multiplying or crisscross things or anything. KCl. That's also aqueous. And then we get the arrow. And then over here, we've got lead 2 again, Pb2 plus, and chloride again. So that's going to be PbCl2. I need 2 chlorines to get a -2 charge to balance the +2 charge. This is a monatomic ion, so I don't need parentheses around it because it's not confusing. So PbCl2, and that is a solid. And then I've got aqueous potassium nitrate, that's K plus and NO3 minus. And those charges are opposite and equal, so it's K plus, oops, not the plus, KNO3, and that's aqueous. Okay, so that's a review of the nomenclature stuff. On a test, it's more likely that I would give you this skeleton formula and make you balance it. Okay, so what often happens with polyatomic ions, often not always, is that the polyatomic ion stays together. So here we have nitrate ion as one of the reactants, and over here we have nitrate ion as one of the products. We can balance the nitrogens and the oxygens separately, or we can think of it as a unit. Okay, so I see that there's 2 nitrate ions over here, and there's 1 nitrate ion over there. So if I wanted to fix the balance on nitrate ions, what would I do? I need more nitrate ions over here, right? So I'm going to put a 2 here. Because now on the left side of the arrow there are 2 NO3s, and on the right side of the arrow there are 2 NO3s. If you look at nitrogen and oxygen separately, I have 2 nitrogens here and 2 nitrogens here, 6 oxygens and 6 oxygens. Well, what about the lead? Pb. How many on the left side? 1. How many on the right side? 1. So that one's good. K. How many potassiums on this left side? 1. And how many on the right side? 2. So I need to increase the number on the left side. So now I've got 2 potassiums over here and 2 over here. Then I need to check the chlorine. Now I've got 2 chlorines here and 2 chlorines there. Usually that last ion will take care of itself. If you've got your formulas wrong, it may be impossible to balance the equation. If I wrote this formula as PbCl instead of PbCl2, then when I had a 2 here for the potassium, I'd have 2 for the chlorine, and when I'd go over here, I'd change this, and then I'd change that, and I'd change this, and I'd change that, and I'd start going in circles. And so that's what you want to avoid. As soon as you realize that, hey, I'm going around and around, stop. Check your formulas, and then start over somewhere else. Any questions?